rational zero function works, the zero theorem works. So here's brief explanation on why that works. I'm just going to use an example of a cubic polynomial, and that's sufficient to explain the general case. So here's a polynomial a3 x to the third, where a3 is not zero, a2 x squared, a1 coefficient x to the first, and constant a0, right? Now we suppose we have a rational zero, x equals p over q. And p and q are integers, right? Whole numbers. Also, if you have number like 2 over 6, you don't leave it like that. You can reduce all the common factors, so you get down to 1, 3, right? So let's assume that p and q does not have a common factor. If so, you cancel those and enter the stage where p and q does not have a common factor at all, right? And we are assuming that that is a zero of this polynomial. So if you plug this one in there, becomes 0. So let's do that. If you plug in there a3, if you raise that to the third power, you see the p to the third, q to the third, right? And plus a2, if you raise the second power into p squared, q squared, a1, p divided by q, plus a0, that should be 0, right? That's the meaning of this thing being 0. And next thing is that because it's about integer question, we turn that into an integer kind of equation. So what should I multiply here so that we clear the denominator? If you multiply q to the third, that's going to cancel that, right? If you multiply that, not only cancel, there's a little bit of leftover, but it still takes care of the denominator. So let's multiply this one over there. What do you see? a3 and p cubed, and denominator is gone. If you multiply that to here, a squared, p squared there, but there's left over one copy of q, right? And if you do that over here, that a1, p times q squared. And if you multiply this one to that, you have a complete q cubed in there. Make sense? These are integer equation. The trick is that if you look at the first three terms, they all have factors of p there, right? So you factor out p. And because this part doesn't matter, I'm just going to abbreviate like that. After you factor it out, whatever the thing in there is an integer, and right hand side is a0 times q to the third, right? Now right hand side is a plus equals 0. Then you can rewrite it like this: p and some of the stuff in there that doesn't really matter in our argument, negative a0 q to the third. There's something called unique factorization into prime numbers. If you have prime integers, doesn't matter how big, the biggest integer that we have written down, whatever, it always factor into prime numbers in unique way. There's no two ways to factor a number into prime numbers. So that's important key statement in here. So in the left hand side, all the prime factors in here appears inside the p must appear in the right hand side because it's unique. There's no way to hide this prime factor. If you look at the prime factorization of this one, there must be p, one prime factor, all appear in here. They cannot go here in the q, because if so, we already eliminated all the factors that are in the p and all the factors that are in the q at the same time. They're all gone, right? So we assume that they don't have any common factor. So if there's any factors here, they must appear here, and they cannot appear in q slot. They must appear right in there, remaining part, right? The whole thing is a0. So all the prime factors inside appearing the p must appear inside a0. That's the part of the rational zero theorem, right? The numerator p must have come from the constant term. So that's one part of rational zero theorem. Second part is actually looking at this one in here. Every q part is a common part, so you can also rearrange it like this: a subscript p, a3 p cubed, plus q is all common, q here. If you factor it out, and whatever the inside after you factor out is like just an integer, and it's equal to 0. So you can see it's arranged like this: negative q and remaining part. So you look at the same thing. Here's all the prime factor that is appearing after your factor. They must appear in the left-hand side as well. They cannot appear inside P because P and Q does not have any common factors. It must all appear in A3. Therefore, everything that in the Q must appear in A3, so Q divides A3, and that was another part of rational zero theorem. So if you're looking at a rational zero, this P must have come from a divisor of A0, Q must have come from the divisor of A3. So if you look at all the list of them, you must be able to find all the rational zeros that are there for that polynomial. Again, there might be, in many cases, this polynomial does not have a rational zero at all.